Check it out now, y'all.
NanoHub U, online instruction.
Hi, welcome back. This is going to be our last week of lectures on electron states and solids. And we're going to start this week off by thinking about the free electron model and improving in a more quantitative way. So we're going to take a lot of the ideas from last week, and we're going to start to evaluate some important parameters that are contained in this free electron model. The discussion that we're going to conduct is found in just about every textbook. So if you're interested in electron states and solids, it's important for you to have a lot of these concepts well understood, because they appear everywhere. So to begin with, let's think a little bit about what this free electron model applies to, which systems it applies. So first, I'd like to introduce that by just reminding you about the structure of the periodic table. The structure basically reflects the S, the D, and the P electrons that we discovered when we discussed solutions to Schrödinger's equation for the hydrogen atom. Right? The fact that there are two columns of elements here reflects the fact that the S shell in these elements are being filled. The fact that there are 10 atoms that span the center region of the periodic table, that's a reflection of the fact that the D shell electrons are being filled. And then out here, we've got P electrons that are being filled. There's 6 atoms in this part of the periodic, in each row of the periodic table in this section, right? Those six atoms reflect the fact that the P shells are being completed. The free electron model provides a reasonably good understanding of the metals that are indicated by the solid white blocks here. In particular, the free electron model is particularly effective in getting out the electronic states for metals in the first row, in the first column of the periodic table. These are the alkali metals, and they're probably the best examples of free electron metals. But the free electron model also does a reasonably good job of sorting out the properties of many of the other metals in the periodic table, and the ones that it does a really good job, or a reasonably good job, are indicated by the white boxes. I think the thing to remember is that the different models that are being developed to describe electron states and solids, right? The various models that are developed involve different approximations to this rather drastic variation in the atomic, interatomic interaction potential energy that the electrons experience. And the free electron model basically is describing what happens to these weakest bound states that are contained in the atomic levels of an atom before those atoms are assembled to make a solid. So the free electron model is basically describing what happens to those topmost electron states. The history of the free electron model, well, it was originally developed around the first decade of the 20th century, early 1900s. The crude approximation is that the core electron states, indicated by blue in this diagram, these core electron states basically shield a majority of the interaction potential energy produced by the nuclear core, the positive nucleus. And so that these outermost electrons, right, these most weakly bound electrons, do not see this rapid variation in the electrostatic potential energy as a function of position. Rather, they see a much gentler modulation of the electrostatic potential energy, simply because the majority of this variation is shielded out by these electrons that are tightly bound to the atom cores. This just means that to a good approximation, possibly, right? To a good approximation, the electrons can be considered as confined in a long potential well. The length of the potential well is given by this parameter capital sub L. And the electron states that were atomic electron states now become delocalized over this well. And the question simply is, what's the nature of these energy states in this well? The model that the free electron model does a really good job, actually, of explaining some of the common features of all metals. And these common features are that metals have a very high thermal conductivity. They have a very good electrical conductivity, so they conduct electricity very well. They have a low specific heat, right? All of these macroscopic manifestations of what we know are good metals, right? They can be explained on the basis of this free electron model. So there's a very good now, in the early 1900s, for the first time, there was a very good understanding of why these properties were characteristic of metals. So the question that we're going to answer in this lecture is, we're going to try to answer how many free electrons really are there in a given solid. So we'd like to know, if we've got a crystal that's let's say in one dimension L meters long, we'd like to know how many electrons are being put into that crystal, and how many electrons are actually free to move in that crystal. That's the question that we're trying to answer in this lecture. So to do that, we first have to realize that if we know the crystal structure, and if we know the lattice constant of a particular metal, then we can actually calculate its mass density from first principles. So this is just illustrated in this slide. We take sodium, which is probably the simplest metal that we can imagine. We do X-ray crystallographic studies, and we learn that sodium crystallizes in the body-centered cubic structure. And by analysis of the X-ray diffraction spots, we can establish that the lattice constant at room temperature for sodium is about 0.423 nanometers. So from that information alone, we can calculate the mass density. And we do that by considering one unit cell, because the sodium atoms condense into the BCC structure, right? We can calculate the mass of each sodium atom. We can count how many sodium atoms there are in one unit cell. We divide by the unit cell, and that should give us the mass density that we measure experimentally for sodium. So we can calculate the atomic weight of sodium. We can look that up. The chemists provide us with that information. So it turns out sodium is about 23 grams for 1 mole. 1 mole contains Avogadro's number of atoms. So that allows us to calculate the mass of one sodium atom. It's about 3.8 times 10 to the minus 23 grams. How many sodium atoms are contained in one unit cell? Well, there's one sodium atom at the center. That's the body-centered cubic structure. And then there's 8 sodium atoms displaced around the perimeter of the unit cell. But each of these atoms is shared by 8 adjacent unit cells. So even though it looks like there's 8 atoms associated with the perimeter of this cubic unit cell, there's really only 1, right? Because they're shared among other nearest neighbor unit cells that are not pictured here. So there's really 2 sodium atoms in one unit cell. The dimensions of the unit cell are given. It's a cube, so we know what the volume is. And this gives when you work through the arithmetic, this gives the density of 0.97 grams per cubic center for sodium. So sodium is actually lighter than water. If you throw sodium into water, it won't sink. How many free electrons are there going to be per unit volume in a sodium crystal? Well, we can also calculate that based on things that we already know. The first thing we have to do is we have to look up what electron states are filled in the sodium atom. So sodium has 11 protons and it also has 11 electrons. So that simply means that the various shells, various atomic shells are filled. Actually, 10 of the 11 electrons are tied up in the 1s, the 2s, and the 2p shells. The most weakest bound electron is now this 3s1 electron, and this is the electron that's going to be given up and free to move throughout the crystal. So that 3s1 electron is represented by these red lines here, right? This is the weakest bound atomic electron. These other electron states, these are called the core states. They're tightly bound to the nucleus of the sodium atom. But these electrons here are going to be free to move around, and those are the only ones we refer to as free electrons. So these guys down here are still bound. They're not free to move, right? It's just the topmost energy electrons that are free to move. So the number of free electrons per unit volume can be calculated as I've shown here, right? We've got Avogadro's number of atoms per mole. We're saying now that each atom releases one electron, and that one electron, once it's released, is referred to as a free electron. This one comes from the 3s1 configuration known from the atomic states. And then we also need another number to convert moles into cubic centimeters. So this is basically a molar volume type of number. And the molar volume can be gotten from the density and the atomic weight. So the motivation for calculating the density on the previous slide is to use it in this calculation. So we now know what the density of sodium is. It's 0.97 grams per cubic centimeter. We know that the sodium has about 23 grams per mole, right? So that gives us the moles per cubic centimeter, and that's exactly what we need in order to calculate the free electrons per unit volume. So when you put the numbers in, I end up with a number that's about 2.5 times 10 to the 28th electrons per cubic meter. And that number, the number of free electrons per unit volume for any element, right, that often is given a special symbol, which is this funny shaped N. So this is the number N per unit volume. It's this 2.5 times 10 to the 28th electrons per cubic meter. I like to compare that number to the number of gas atoms per cubic meter that are present in the air surrounding this room. So if you do that calculation, you find out that there's about 1,000 less gas atoms per cubic meter than there are electrons per cubic meter in a metal. So these electrons per cubic meter are really dense. They're about 1,000 times more 1,000 times more electrons per cubic meter in a metal than there are gas atoms per cubic meter in air. So there's a lot of electrons moving around. I think the important formula for this lecture is this calculation of the free electrons per unit volume. I just write the formula down so it's easy for you to access and remember. I think there's a homework problem where you're going to have to calculate this for a number of different elements. And so you need to know for each element in the periodic table, you have to know the number of valence electrons per atom. Those are the most weakly bound electrons from the atomic states of electrons in atoms. You need to look up the mass density of a particular element. Avogadro's number is a number that you know, and you also have to look up the molar mass. In other words, how many grams per cubic centimeter is required. you know those numbers, then you can get the number of free electrons per unit volume in a pretty straightforward fashion. And it turns out that's an important number to know, right? That's an important number to know, and that'll become clear as we move through this week of lectures. So with those preliminaries out of the way, we can basically ask, what are the solutions that Schrodinger's equation allows? So now we're going to start to think in 3 dimensions. So we have to write Schrodinger's equation down in 3 dimensions. We've now got an approximation for the interaction potential energy in terms of these plane waves, e to the I, g, n, r, right? The g sub n's are the reciprocal lattice vectors. And basically we're trying to solve this differential equation for the allowed energy eigenvalues E that characterize the electron states in a solid. So for one electron, the situation is pretty simple because we'll just have one electron. It'll be at some location X, Y, and Z in a coordinate system, and it's going to be moving in the electrostatic potential energy generated by this periodic array of atoms that are surrounding that one electron. So that is the one electron problem. Unfortunately, we've got a lot more than one electron, so we have to start to think in a systematic way how things are going to evolve as we start to add, let's say, 2, 3, 4, all the way up to n electrons per cubic meter into this solid. So let's just think for a minute about the 2-particle approximation, right? This is something that we've already discussed back in the 7th week of the semester, right? So now what we have is we have 2 electrons. One electron is at position 1. The second electron is at position 2. And we have to write a Hamiltonian, H, that includes the interaction between electron 1 and electron 2, in addition to the periodic electrostatic potential energy introduced by the lattice of the periodic lattice of atoms, right? And of course, this periodic lattice of atoms is going to be one of those 7 crystal systems that we discussed. So writing down Schrodinger's equation for this problem starts to become almost overwhelming right from the beginning. The real problem involves a Hamiltonian that contains the interaction between particles 1 and 2, and it also contains a 2-particle wave function, right, that has the proper symmetry to reflect the fact that these electrons are fermions. That's a very difficult problem to solve, right? And so what we often do is we say, well, we'll pretend that particle 1 and particle 2 are independent of one another. That allows us to then write down 1-particle wave functions in this form, right? And so in principle, this is a much easier problem to solve than this, right? And if you understood the discussion in week 7, then you'll have an appreciation for the comparison between a single particle solutions and the exact solution, which is contained by this symbolic equation. So you have to possibly review lecture 7 in order to understand the fine points right here. What do we know about these 1-particle solutions? Well, to a first approximation, the Hamiltonian then breaks down into two terms. One term just contains the coordinates of particle 1. The other just contains the coordinates of particle 2. And the wave function for this 2-electron system is then defined as the product of the spatial part of the wave function times this term, which contains the spin part of the wave function. And this spin part of the wave function is asymmetric under particle exchange. So it's got a spin up and a spin down wave function, and it also contains the possibility that particle 1 and particle 2 are interchanged one with respect to another. When they're interchanged, then the spin of particle 2 flips, the spin of particle 1 flips, right? And so this is the asymmetric term that has to be included to properly account for the Pauli exclusion principle, which governs fermions. And since electrons are fermions, it's important that be incorporated. So with these two approximations, right, then you can write down Schrodinger's equation, and you can see that because the Hamiltonian doesn't contain any interaction terms, it just contains terms that are explicit functions of coordinate 1. It contains another term which is an explicit function of coordinate 2. When you operate this Hamiltonian on this wave function, this is the spatial part of the wave function, right? You end up with terms that look like this. And of course, H1 times psi1 just gives the energy E1. H2 times psi2 just gives the energy E2. And plus the wave function back itself again. And what you conclude is that for two particles, right, the total energy of the system is the sum of the one particle wave functions. So the total energy is the sum of one electron energies, and that it becomes a much more tractable problem to discuss. So the idea is you can extend this to n particles. The formalism gets to be complicated, but what you'll find at the end of the day is that you'll have a sequence of operators that operate only on wave functions with the coordinates associated with the coordinates in each term in the Hamiltonian, and the end result is that the total energy of the electrons in the crystal just become the sum of these one electron energies. So this is a first approximation to solving Schrodinger's equation for this very complicated problem that involves something on the order of 10 to the 28 electrons per cubic meter. What we're going to do is we're going to focus on the single particle energies, and we're going to add up those energies to get the total electron energy in the system. So this is kind of a general introduction to where we're going to go. We're going to derive in the next lecture a sequence of parameters that are characteristic for each element in the periodic table. And these parameters that we're going to derive are going to describe some of the important properties that characterize these electrons within this free electron model. So come on back to the next lecture, and we'll discuss those parameters, and we'll show you how to calculate them, and we'll try to explain why they are so important in characterizing electron states in solids.